Right, welcome back. Second homework on our thermodynamics course. Hopefully you watched the first homework, so I don't need as much introduction. But basically this homework is on energy and different aspects of energy. Energy transfer, internal energy, enthalpy, and all that good stuff. Okay, so the second problem says, in class we talked about steam near saturation is more dangerous than very high temperature steam. And that's because of latent heat. You know, when you're close to steam condensing, well, that steam is more likely to just burn the snot out of you because it's so close to condensing. So that's why you need to be very careful around steam. But it's when it's near saturation, like a boiling pot of water, that's even more dangerous. Okay. Now, that has to do with rates and other things, which is more heat transfer than thermodynamics, but I still kind of want to illustrate some of these things through hexane. Okay. So, assuming the heat of vaporization for N-hexane, so delta H vape is equal to 28.88 kilojoules per mole, not kilojoules per kilomole, kilojoules per mole. It's really not a lot, which is a lot. I mean, you know, a mole is not a lot. At 341.95 Kelvin. Okay. How much would the enthalpy change by heating up the hexane from 300 to 400 Kelvin? Compare that to heating it up from 400 to 500 Kelvin. Okay, and so, well, we've got, you know, delta H, okay, and so we're going to be basically going through a pathway. Now, we're going to talk about pathways a lot more when we get into departure functions, but I think we mentioned it, so what we're going to basically do is say, okay, I'm going to heat this up, delta H, okay, I'm going to have some, temperature difference here. I'm going to heat this up as a liquid, and then I'm going to bring it over to a vapor, okay, and heat it up some more, okay. And there's, a delta H according to this, there's a delta H according to this, and there's a delta H according to this. This one obviously being just the temperature increase of the liquid, this being the temperature increase of the vapor, and this being the temperature increase, well, not the temperature increase, because temperature shouldn't increase during the phase change. This is the enthalpy increase associated with it boiling. Okay? Now, it doesn't say anything about heat capacities. Nope. So we have to make some assumptions. Okay, we're going to assume, delta, because I'm going to need heat capacities. I have temperature changes, I have enthalpy changes, and so we're going to assume that the heat capacity of the liquid is constant. Okay. We're not going to assume it for the gas, but we're definitely going to assume it for the we're going to definitely assume that the heat capacity is constant. Okay. Now this was stated as a fact. Okay. So I don't need to make any assumptions associated with that guy, but I do need to make an assumption associated with the heat capacity being constant. Okay. And so I probably need to look up that heat capacity. Okay. I don't know what it would be, but I need to look it up. Okay. So again, this is more of a problem to kind of see, how a different thing is. But the point of these videos is not to do the calculations for you. It's just to show you how things work, and you can. I assume you can plug in numbers and look up numbers. So, but let's say I wanted to look up the heat capacity of hexane. So I go to my good friend who? That's right, Google, possibly NIST. So let's go to NIST. NIST hexane. Yeah. So, and then I want, let's hear, condensed phase thermodynamic chemistry data. Okay. It looks like I have heat of formations. Oh, here we go. I've got heat capacities at all these good temperatures. And I got a lot of different ones, and so it's typically best to use one that's more modern, but there's so many, I kind of just just pick one that seems reasonable. So it looks like they're all hovering around 196 though. So CP of liquid is about 196 joules per mole K. Okay. So 196 joules per mole K is approximately the heat capacity of the liquid. Now for the vapor, we can look that up in the back of our book. Okay. But what we have is we have all these and they add up. Now it doesn't matter what path we take. No, I mean as long as we get from here to here, that's going to be good. So our our total delta H is basically going to equal Cp of the liquid dt from T1 to the boiling point plus the heat of vaporization. Okay. So it's going to get up to the boiling point, and then it's going to vaporize, and then I'm going to go from TB to T2. Okay? And that's going to be the Cp of the vapor dt. Okay? Now we assume that the Cp of L is constant, so I can pull this one out of the integral. I cannot assume that one's constant, or at least I'm not going to. Okay? And so if we need to go into our book, and let's see here, table A2, and we're looking for hexane, normal hexane, and hexane. Okay, so we have, so A is equal to 3.025, B is equal to 53.722, and then of course C is equal to negative 16.791. Okay. And this is 10 to, this is just that. This is 10 to the minus 3, and then this is 10 to the minus 6. Reading the table as it's supposed to be. Okay. But again, they're just numbers, but I'm helping you, okay, how am I supposed to read this stupid thing? That's how you read it. Okay? So let's look at, okay, so let's break this up, or let's start boiling this thing down. So remember that Cp of a vapor, or of an ideal gas rather, over R is equal to A plus BT plus CT squared plus, I think it's D over T squared plus E T cubed. That sounds about right. Something like that, but that's 0, so we just have that one, okay, which is totally fine. So, and that's Cp over R, so we're going to have to multiply that whole thing by R, okay? So delta H, so this one, well, this is really our picture. Our pathway's our picture in this case, okay? We don't really need a system, it's boiling. Our picture's our pathway, we have our assumptions. I don't think there's really anything else to assume at this point. So delta H equals, so we pulled that out of the integral, okay? So we have Cp of the liquid, integral T1 to Tb dt, plus delta H vape, plus from Tb to T2, okay, we're going to have an R out here, well, we're going to have R times A plus B T plus CT squared dt, okay? And then, we're going to go to the next step, and we'll just kind of integrate it all in one step. So we have CPL TB minus T1 plus delta H vape plus R times A times T2 minus TB plus B over 2 T2 squared minus TB squared plus C over 3 T2 cubed minus TB cubed. Alright. And at that point, I plug in a whole snot of numbers. Okay, I mean at this point it's just plug and chug. Okay. But I've shown all the work. And you might be like, man, that's a lot of numbers to plug in. Well, remember, if you have a heat capacity calculator in your computer, you can use that to do this. Now, I do want you to show the math. I do want you to get to that point of the math. I want you to recognize where the math comes from. But in terms of the actual calculation, well, you could just, plug that into your computer, and I'm okay with that. Okay, I don't mind you doing that. Okay. The other thing I want you to do, though, is I want you to see kind of how things compare. Okay, so this was 28.88 kilojoules per mole. Okay, 196 times. Okay, our temperature difference. So that's 341. So about 40. We got 40K worth of. So 40 times that is, I don't know, about 8 kilojoules. 8 kilojoules. It's not even a seventh. Wait, well, 8. It's not even a third of the heat of vaporization. 40K worth of temperature change, okay? And the other one's going to be 60, and this is probably going to be less because it's a gas. Because the heat capacity of a gas is a whole lot smaller than the heat capacity of a liquid. Okay. You can always kind of approximate what the heat capacity of a gas is by the A term, because these are just more fudge factors. So you got 3. Well, 3, times 3 times 8 for the gas constant is 24. 24 joules per mole K. That's 196 joules per mole K. It's a tenth. So the heat of vaporization is dominating here. Okay. Now the other part of the problem says, what does it say? Compare that to heating it from 400 to 500. Well, 400 to 500 is just the gas part, so it really just, you rederive it, or just say, okay, well, it's the gas part, just the temperatures are different, that's fine. You've derived it once, you've demonstrated the skill, it's okay. But, make it very, very clear that you understand that, okay? And then, of course, you integrate that, but again, 100K, but the heat capacity's a tenth. So it's only like I increased the liquid 10 degrees. So you can see how different it is between a liquid, a vapor, and during vaporization. Okay, but I'm going to let you do the math on your own.